Hello everyone and welcome to a new LS-DYNA tutorial. Today we will do the 2D compression of a structure, a quasi-static 2D compression, and the structure that we will study today is an auxetic structure. An auxetic structure is something that has a negative Poisson ratio. So without further ado, let's get started. So here I have the IGS files already. So I copy one of them and put it in a different folder. Then I will open my LS prepost. Here I'm using 4.11. Okay, waiting for it to load, and then I can just drag and drop, and the units just keep it as default, which is mm. All right, now we go to mesh or to measure, and then select the size option, click on one face. As you can see, it is a 3D, but we want only one face. So if I click there, compute and mesh, the size is a bit big, 0.5 mm, and try to mesh. Okay, you can see here, this is quite okay, but maybe I want to refine it more. So here I put the size 0.25, mesh. Okay, this seems to be acceptable for me. And click on accept. Okay, now we have the structure. I can just delete the IGS file or the shape file because I do not want it anymore. Next, I will go to, next I measure that coordinate, and the coordinate of Z is 1, so it needs to be 0. So I measured that and I found the Z coordinate 1. So I will translate it negative Z1, 1 millimeter in the negative Z. Then I measure again, and as you can see, the Z coordinate is 0. Because we are doing 2D analysis in LS-DYNA, and the requirement for that is that all the nodes are on the Z axis. I mean, all the nodes in the XY plane, which means Z equal to 0. Now I go to the shape measure and auto measure, and I will do like this, select the 4 points, and then create the mesh. I hide the structure, and then I just choose a suitable number of elements here. Okay, maybe 100 here. Okay, 120. Click accept. Okay, this is good enough. The thickness is 0.43 for the height. So I need to move it up with the same height in the y-axis. When we're talking in 2D, height mean in the y-axis. Okay, so here I need to extend a bit to the left and the right. Okay. But before that, maybe I want to move it down. Okay, I want to make the bottom plate. This is the top plate. Now I want to make the bottom plate. I measured the distance already from the measure tool. You can click just on F4 for the measure tool to pop up. Now I go to transform, and then select the top plate, make a copy, and then I translate, and you can see I have a copy down there. Okay, we want to make a node at the center of the model. So now I have the X and Y coordinate. And next, I want to make it larger in the X direction. So I scale in the X direction. So instead of creating a new elements on the left or in the left and right, I just expand it. Okay, now I select the bottom plate and put it a different ID. And here I just change the part ID or the part name here to be top plate. And here also I change the name to be specimen for my structure, or I can just change the name from here. Okay, now I think I'm done with the meshing. I need to save this. So Control S and make sure to save as .k, not .igs. Okay, close and just save. All right, so I have the meshing file done now. So I will create the input.k file or the keywords file. So to do that, I have more than one method. And here I just copy paste this one to make it easy. And then I will rename mesh.k and input.k. And here, this is the input.k file. I will delete everything, delete the parts and the nodes and everything. And you can see we do not have the mesh or anything else. So here I will just define one thing, which is a control termination, 0.1. And the time step, this is just defined with the default parameters. We will change it later. Okay, the section, it will be a 2D analysis. So section shell, and the element formulation, it will be number 13. And for integration points and the thickness, I can leave it as 0 because it's a 2D analysis. Okay, I will save this. Yes. I will close the input.k and then I will right click and open with the text editor. And then here enter new space star include mesh.k. Then Control S to save. Okay, now if we open the input file, input.k, you will see that okay, we have a warning here because we have a duplicate duplicate node, which is the center node. That's a warning. But you can see we open the input k and the mesh pop up. So here I open again with the text editor, and this is, I need to delete this node. This is what caused the warning. Control S save. Okay, now I open the mesh and I will check the part. Okay, so here I will delete the start part and paste it here. I will copy from there and paste it here. So the mesh.k has only the element and the nodes. Section ID is 1 because we already defined it. Okay, now for the material. For the material, instead of defining it, I will just copy paste from a different model. I'm looking for that model now. I will right click. This is the model that I want to copy from. And then we will go to material and copy the material. In the find or in the search, I will type *mat *mat. Okay, we have the material that we want. Okay, the two rigid materials for the top and the bottom plate, and also material piecewise linear plasticity for our Auxetic structure or our specimen. So here I copy from there and I paste, and I will change the ID. So the top plate will have material ID number 2, the bottom plate will have number 3, and the specimen will have material ID number 1. Okay, here I'm just copy paste from the same file. I'm just rearranging it. This is optional, you don't need to do it. So here I will put this on my other screen. Now we go to our main file here. Okay, so this is our file. So now I will double click here just to check everything is fine. So no warning, nothing, means that I copy paste correctly and there is no syntax error. And now if I measure here, you can see the total height is 55.9 or 55.7, around this value. And now if I go to here, click all, and we want to define the curve. Okay, so this is a displacement curve. Time equal to 0, displacement 0, time equal to 0.1, that's the total displacement. And then I will scale the y-axis, which is the total displacement. So here I'm putting, for example, let's say 0.8, meaning 80% of the total height. So here, if I plot this, I will get this displacement versus time. Accept. And then I will define this. Sorry, I will go to boundary condition. Where is that guy? Our friend is here. Boundary, prescribe, motion, rigid. New ID, number 1. And here is the top plate. It will degree of freedom 2, which is y. VAD equal to 2, which is displacement versus time curve. So select the curve ID, and the scaling factor here I put -1 so that it goes downward. This I can put a title, top plate motion. Material, okay, just double checking. So the top plate is able to move in Y, and the fixed bottom is fixed in Y, in X and Y. So the boundary condition for the plates are correct. This is the ABS, and as you can see here, the units of the material. The units of the material are in standard SI units, meaning the length should be in meter, not in millimeter. So I save that. Then I put here, I go to the curve again. In the scaling factor, I need to put E minus 3 here because I just realized the length according to the material, the length should be in meter, not in millimeter. So here I'm scaling the displacement curve so that it is in millimeter, not in meter. And then I'm scaling the model itself. Scale in X and Y, and the scaling factor is 1000. And then I select everything, select by part, select whole, and then scale down. It becomes small. I click on accept. Then I auto center. Okay, now this is after I scaled. I click on F4 for the measure tool. I click the top and the bottom node here, and you can see now the distance is 0.0557. So I've changed it from millimeter to meter. Okay, next, I will create a contact now. So contact 2D. Where is that 2D? Contact 2D automatic surface to surface. This is the one. New ID, title, optional, but it's better to put it. Honeycomb to top plate. And then here I need to define a set part. So new entity creation. So here I put honeycomb or HC. I click on the honeycomb or the Auxetic structure. And then now I will define this similarly. I will define the top plate. Click here. Then I put top plate. Then click apply. Okay, now click on accept. Okay, I'm just defining the friction coefficient, static and dynamic. Click accept. Now click on new ID. Now honeycomb to bottom plate. Need to change the set part from top plate to bottom plate. So click here, we create a new one. And then I zoom in and click on the bottom plate. Click on apply. Now accept. So now we are done with the contact. Okay, automatic single surface. Automatic 2D automatic single surface for the honeycomb contact with itself, so that the legs or the struts of the honeycomb comes into contact with each other and do not pass through each other. So we put only the slave segment set and the friction coefficients. Okay, next I go to part. Just want to double check everything. Okay, so here I'm checking the properties. Seems to be okay. So Control S to save. Okay, done saving. Okay, now we need to define the termination. 0.1 second is okay. Okay, now the database. So instead of defining as usual, I will just copy paste from here, which is much faster. So I have the database boundary output, the global statistic, material summary, rigid body output, and reaction forces. I copy from there, and then I just paste here. Okay, you can see dt to ms is applied, meaning we're applying mass scaling. So I control saved already. Now our file is ready to be run. We run the input.k, not the mesh file. The input.k will include or it will call the mesh.k file. So you can see here the percentage increase is 1.136 e power of 4, which means it is very, very huge. And okay, we will open the D3 plot. Okay, open the D3 plot, not the keyword file. Okay, you can see the compression is working, the contact is working, seems to be okay. And you can see actually with the with the compression, the width of the overall width is becoming smaller, because that's the definition of auxetic structure. Okay, so I will open again. Maybe now I will show some of the results. Go to the ASCII option, and here, let's say, go to the history part and click on the energy of the part. You can see here the kinetic energy is very small, which means that we can accept this as quasi-static. Okay, so you can see it's running. We'll just wait a bit here. Okay, you can see we have error termination. This means maybe we are applying too much of mass scaling. So open this, the results. Too much mass scaling, meaning the time step size is too large, which causes the numerical instability. Okay, especially here we have the contact. The contact needs sufficiently small time step size. So here we have the compression. You can check the energy again, and still again we see the kinetic energy very small or very almost zero. So that's the criteria to accept this as quasi-static. Okay, we see the reaction force here in the y direction. Okay, it's negative, so maybe we take the master instead of the slave. Okay, so this is our reaction force. So maybe I will save this, not load, save. And here I will put the name force, and the format is CSV, single axis. Save. Okay, done. Now go to the part, or go to ASCII option, boundary output. I can also check the forces from here. So here I have Y force again, or I will check this rigid body output. Now to plot the displacement, we already have the force, so this is the displacement. So I click plot and then save displacement and type the name and save. Now go to the XY plot force, and then I can click cross, then X and Y, select the displacement and the force, and here I have the force displacement diagram. So put the name force displacement, save. Okay, I can change the label. Here the force will be Newton per unit length. Okay, because this is a 2D analysis. Newton per meter. So if your specimen is 1 meter width, then you can multiply this by 1 meter. And this is the displacement. and it is in meter. And click and accept, and then done. Okay, that's all for this tutorial. Thank you very much, and see you in the next one. Have a good day.